So I'd like you now to keep that previous problem in mind, because we're hopefully going to come back to that later and make some comparisons with the new type of motion we're learning about. So I've said here for our notes that so far we have solved problems involving linear motion, motion in a straight line, similar to that car problem, same as that car problem, and projectile motion. And this is motion that follows a parabola. We're now going to look at circular motion. And it's no surprise that the definition here, circular motion, is any motion taking or following a circular path. What I'd like you to do now for me is to pause the video, and I'm going to ask for a little bit of space for this because we're going to come back and add some annotations to it. I'd like you to start a mind map, and I'd like to think about as many objects or as many things as you can that experience circular motion. So you can pause the video now and have a go at that. Okay, so here are some examples, and these are the examples that you typically face in terms of solving problems, and they give some of the best examples of circular motion. So first one, and you're going to see this with Mr. Davis later this week, is orbits. Now, this can be the orbits of planets around stars, satellites. So you can have natural satellites, which are things like the moon, and artificial satellites, which are the sort of thing Elon Musk puts into orbit. These generally follow near enough perfect circular orbits. Planets are an interesting one. In our solar system, with the exception of Mercury and Neptune, the far outer planets, the planets follow a very closely circular orbit. It turns out that the orbits of the planets are actually elliptical, which is a squashed version of a circle. But for a lot of what we are going to do, it works to apply the idea of circular motion to them. For the orbit of the Earth, for example, the orbit is very close to being circular. So we've got planets and satellites. We've also got more practical examples or more down-to-earth examples. If you've got a car on corner or roundabout, we've got this idea of that undergoing circular motion. In addition to that, you've got things like fairground rides, so that includes roller coasters, loop-the-loops, carousels, all that sort of thing are undergoing circular motion. So those are three key examples there. You can think of more, you will come across more, but as we go into this topic in more detail, it will be these things that we look at and give you a way of approaching any sort of thing that's undergoing circular motion. Now, when we looked at linear motion or motion in a straight line or projectile motion, we used certain terms to describe that motion. So when we looked at linear motion, we didn't call it linear motion, but when we looked at it, we saw that we could describe it in terms of displacement, velocity, and acceleration. And those were the three things that we kept coming back to when describing the motion, and they're the things that we look at in the Suvat equations when we're solving problems with that. Now, we can describe circular motion with these terms as well. In fact, we will go on to do that. However, with circular motion, it also helps to introduce some new definitions. And the purpose of these definitions is to make it easier for us to describe objects undergoing circular motion. So we've had these things for linear motion. For circular motion, we can define three more things. We can define, instead of the displacement, the angular displacement. Instead of the velocity, we can talk about the angular velocity. And instead of the acceleration, we can talk about the angular acceleration. And just as these are given symbols in equations, our displacement is given the letter S, velocity V, acceleration A. These are given symbols in equations too. So angular displacement most often is given the symbol delta theta, change in angle. Angular velocity is given the Greek letter lowercase omega, which is drawn like that, not W. And the angular acceleration is given the Greek letter, again, lowercase alpha. And these help describe circular motion. Now, something I want to make clear at this point, these are not the same things. I've written them as like a comparison here, but they aren't the same. I'm not saying here that displacement is the same thing as angular displacement. I'm not saying velocity is the same thing as angular velocity, but they are linked, and hopefully in the next section you will see how they're linked. In a lot of cases, these angular displacement, angular velocity, and angular acceleration are said to be analogous to displacement, velocity, and acceleration. And that means they kind of follow the same pattern, but they aren't the same thing. So just to review then before I finish this quick section, for linear motion, we've described it in terms of displacement, velocity, and acceleration. And we can use these terms to describe circular motion too. It's often easier to describe it in terms of these three quantities here. So angular displacement, angular velocity, and angular acceleration. And we're going to see in the next video that whilst these aren't the same, they are linked. And thinking about them in a comparison like this will help you remember them as well.